Hey guys, today's lesson is operations with polynomials. And the goal is by the end of this lesson, I want you to be able to say, I can graph polynomial functions and I can identify key features. So to begin the lesson, we're going to do this warm up. I'd like for you to pause the video and just go ahead and try this. So hopefully you paused and we're going to go over it together. But it says name which one is a third degree polynomial function. So I know that this is a polynomial function of the first degree. I know this is of the second degree, and it just goes in order. This is of the third degree and this is of the fourth degree. So another way that I would have to know that it's a third degree polynomial function is third degree tells me that one end's going to be up and one end's going to be down, right? Because that's an odd number. And the degree tells me that one end should be up and one end should be down. So it has to be C. It can't be B or D. And we know A is linear. So that rules it out and narrows it down to C. Okay, we're going to look at in a little bit more detail of how to know that today also. Okay, so a negative leading coefficient. Think about negative. I like to just think about parabolas and linear equations. I know that a linear equation has a line that goes like this. It's going down. And of course, both ends are down on a quadratic that has a negative leading coefficient. So thinking about these ends, it starts with one end up and ends with one end down, or it's both ends down. So that wouldn't be A, could be B, right? Could be C, would not be D, because C begins with one end up, ends with one end down. So that's like a linear function. Okay, and the domain and the range are all real numbers. So this, as x goes up, y is going up. As x goes down, y is going down forever in both directions. So I know that it has a domain and a range of all real numbers. While b has a domain of all real numbers, as x, x can get bigger and bigger or smaller and smaller, but it doesn't have a range of all real numbers because you can see that there are no y values up here. They're all going to be down here. C has a domain and range of both all real numbers. And again, like B, D only has a domain of all real numbers, but the range is never going to be below these values. So there's no y values down here, therefore it's not all real numbers. It says which of the following has end behavior that as x goes to positive infinity, y goes to positive infinity. So clearly A is one. Not B, because as x goes to positive infinity, it's going down. Same thing with here. As it goes up, it's going down. As x goes up, y goes down. Here, as x goes up, y also goes up. So it is A and D. And which one has no real zeros? Well, what are zeros? It's where the parabola crosses the x-axis. So A has real zeros, C has real zeros, D has real zeros. The only one that doesn't have any real zeros is B. So hopefully that made sense. That was a good little review. And if you had any questions about this, jot it down in your workbook and let me know. Shoot me an email at the end of the video or pause the video and do it right now. But let me know if something here didn't make sense and I will be sure to explain it in more detail. Okay, it says you can estimate the zeros of a function by using a graph. Well, how? What we do is we're looking for the values where the y values change from negative to positive. If my y values change from negative to positive, then clearly it has crossed the x-axis. So my zeros are where it crosses the x-axis. And it's important to note that the graph of a polynomial function of degree n has n zeros, although not all of them may be real. We looked at this in class and we kept coming up with ones that didn't have real zeros. And it's important to notice that it says it has, let's see here, let me read this again. The graph of a polynomial function of degree n has n zeros. That means if it's something like x cubed, that it could have at most 3 real roots. It's not going to have more. It could have less, but it will not have more than 3 real roots. 3 real places where it crosses the x-axis. So let's try this. Example 1. Determine the consecutive integer values of x between which each real zero of the function is located. Then draw the graph. So what I would like for you to do is take the time to plug this in. Make sure when you plug it in, you put it in parentheses. So I've got the whole quantity, negative 2 to the fourth power, minus 2 times negative 2 cubed, minus negative 2 squared, plus 1. Type that in to the calculator and fill in your table. All right, so looking at this, I see some important numbers here. When I go from 1 to negative 1, there's a sign change, right? From here to here, there's a sign change. And again, from here to here, there's a sign change. So that tells me that between these consecutive integers, 0 and 1, and again between 2 and 3, there was a sign change. So that means that I've crossed the x-axis. There's a root in there. There's a 0. So let's go ahead and graph this and look at it. We've got a rough sketch of the graph, and we can tell that what's happening as x goes to negative infinity, my f of x is going to positive infinity. As x goes to positive infinity, f of x is also going to positive infinity. So both ends are going up, which we knew was going to be the case because this is an even coefficient with an even exponent with a positive coefficient. Got to get my vocabulary words right here. So the number in front of the x is positive. That tells me that it ends going up. And the fact that it's an even exponent tells me that both ends are going to be doing the same thing. So since it ends going up, both ends are going to be up. So here's my graph, rough sketch, both ends are up. The leading coefficient, we can see that the sign change here is where it does cross the x-axis in between these sign changes between 0 and 1, and again between 2 and 3. Those are where the zeros are. That's where it crossed the x-axis. And we expected that it would cross no more than 4 times. It only crossed 2, so that's not more than 4. All right, so looking at extrema, the extrema of polynomials, extrema occur at relative maximum or minima. It's exactly what it sounds like. Maximum is the highest point in regards to the points on either side of it, and minima is the lowest point with regards to the points on either side of it. Sometimes these points are called turning points because if you look at it, the graph is changing directions. And when we're looking at this, the graph of a polynomial of degree n has at most n minus 1 extrema. So looking back at this one, x to the fourth is going to have at most 3 turning points because 4 minus 1 is 3. So look at my turning points. 1 turning point, 2 turning points, 3 turning points. Did not have more than 3 turning points. So this is good. This follows along with what this is saying. So when we're looking at the extreme of polynomials, we want to identify key features. Look at the degree of our polynomial. Look at the leading coefficient. Make a table just like we did up here. Then graph it. Then check the end behaviors. Check the zeros. Check the turning points. And make sure that it all matches. Okay, so I'm going to go ahead and pause and I'm going to fill in my table. I encourage you to do the same. Okay, so there's some things I want to look at before I start graphing this. This is a cubic function, right? The degree is 3. So that tells me, since it's an odd number, that one end's going to be up, one end's going to be down. And the fact that the leading coefficient is a positive number tells me that it's going to start down. Some things are going to happen, and it's going to end pointing upward. I have a general idea of what it's supposed to look like. Okay, the other thing that I know is that because this number's 3, well, 3 take away 1 is 2, so that means it's going to have at most 2 turning points, right? And because this number's 3, that means that it's going to cross the x-axis at most 3 places. Might not all be, there could be some imaginary roots, there should be real roots, but there cannot be more than 3 real roots. So let's kind of sketch this graph out now and see if our graph matches what we thought that it should look like. Okay, so here's my rough sketch. So we expected there to be at most 3 zeros. We've got 1, 2, 3. Okay, we expected there to be 2 turning points, 1, 2. We expected it to start with one end up and end, or with one end down and end with one end up, and that is exactly what happened. So we could tell a lot just by looking at the function. We knew a lot of things about it. And when we made our table, we knew that there was going to be a 0 between -3 and -2, right? Here's -3, here's -2. It crosses there somewhere in between. We knew there was going to be another one between -1 and 0 because, again, it switched from a positive to a negative. And we knew there was going to be another one between 1 and 2 because it switched from a negative back to a positive number. So actually, it is the 0. But so we can see, we can learn a lot just by looking at the function. And then when we graph it, we can match and make sure that what we thought and what actually happened match up. So the last thing I want to look at is I want to analyze a polynomial function. So talking about insects, it says the brightness of a firefly's light is related to the temperature of its environment. That's pretty cool, isn't it? The intensity of the light measured in lumens is approximated by f of x equals -0.1x cubed plus 0.4x squared plus 0.3x plus 10, where x is the temperature in degrees Celsius. So we're going to begin by completing the table. I don't know why it jumped screens on me again. But anyway, back over here. So what we're talking about is, I picked up the wrong marker. We plugged in the numbers. We're talking about the intensity of the light. So if it's 0 degrees outside, the brightness is 10 lumens, all the way up to 40. If it's 40 degrees in Celsius, it is 20 lumens. Now look what happens. It looks like it's going up, 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 up. And then once it gets to a certain height, it starts going back down. Well, looking at the function, I see that it's got an odd exponent and a negative leading coefficient. So that tells me that it's starting with one end up and it's ending with one end down. And we expect 2 turning points because 3 minus 1 would be 2. So I expect 2 turning points. So I'm thinking it's going to look something like this. Let's check it out and see if we plot these points. 0, 10. I'm going to go ahead and pause this again while I plot these points, and I would like for you to be doing this on a piece of paper as well to follow along. Okay, so I did a horrible job of connecting my points, but I've plotted them. And as we were looking at up here, it looks like it's meeting my expectations. Like maybe, this end doesn't look quite right, but if we were to look at some negative values, then, it is going to go that way. But think about why we wouldn't even consider the negatives in this problem. We could have negative temperatures, right? The temperatures could go in the negatives. So maybe we should have considered it. We could have -degrees Celsius out there. It wouldn't make sense to consider negative brightness. We wouldn't want to go beyond this point and keep on going down because that doesn't make sense. But we could look at our function and extend it on out this way because we could have negative temperatures. Okay, so what is the relevant domain here? Well, the relevant domain could really be all real numbers. But considering the fact that a firefly probably isn't going to be alive in temperatures much lower than 0 degrees Celsius, we're just going to focus in on the temperatures that it gives us. So my relevant domain for this is x such that x is between 0 and, at this point, we went up to, what was it, 40, we'll just say 40. So my x values are from 0 up to around 40. Okay, the relevant range. So what are the values of y that we looked at? So it looks like my range started here at 10. And it goes way, way up, and then it keeps on going down forever and ever and ever. So what is my range values? Well, let's look at the highest point. My highest point was 111.12 at 25 degrees Celsius, and then it started going down. So I would say that my range would be y values that are less than 112. And I want to know, where does the maximum occur? Well, it looks like it occurs somewhere in between here, between 25 and 30 degrees Celsius, right? It's happening right in here somewhere. So between 25 and 30 degrees Celsius. What's my y-intercept? It's this 10. What's my x-intercept? Well, we really don't know. It doesn't show us the x-intercept here on the graph, but we can assume that it's going to be this, if it continues this pattern, it's going to be somewhere here between 40 and 45. And does the graph have symmetry? No, there is no line here that we could cut this graph in two and that it would make a nice pretty reflection of itself across it. So that takes us up through this lesson. This was kind of rough. I think I fumbled through it a little bit. Hopefully I didn't bore you guys to tears, but it is important to be able to look at graphing the polynomial functions and to be able to identify the key features, and hopefully you're able to do that now just by looking at the function itself.